For optometry, you can really just use the exact same thin lens equation stuff we've been looking at already. It's just, you got to be very careful about how precisely you apply it. For any optometry situation, if you have vision problems that need to be corrected, the main ones we're going to be looking at are nearsightedness and farsightedness. Typically, either you can't focus on things that are far away, so anything further than a certain distance looks blurry, or maybe you can't see things that are too close. Things that are far away look fine, but if it's too close, if it's closer than a certain distance to your eye, it looks blurry. So this leads into the idea of the near point and far point as terminology. The far point is the furthest distance you can see clearly. So anything further away than that is going to look blurry. And ideally, you'd like to be able to see things that are how far away? 20 feet? I mean, that's a good start, but ideally you'd like to be able to look at things further away than that, right? Oh, by the way, the 20/20 and 20/20 vision, if I remember correctly, that specifically means 20 feet away, you can still see clearly enough to read 20-point type, 20-point letters in terms of the font size. But that doesn't mean you can't see anything further than 20 feet. Maybe you can't really read letters that are more than 20 feet away, but ideally you'd like to be able to see things that are very far away. Like you want to be able to look at a building off in the distance, or a mountain on the horizon, or even the moon or a star, which are how far away, effectively. Essentially infinitely far away, yeah. And of course, they're not truly infinite meters away. It's just that they're so far away compared to the other distances involved that we treat them as effectively infinitely far away. So ideally, we want the far point to be infinity. Optimally, we want this to be infinity. You'd like to be able to see things that are extremely far away. Not necessarily be able to read 20-point font on them, but to be able to at least see them reasonably clearly. The other extreme is the idea of the near point. If you hold an object closer and closer and closer to you, at some point it's going to start to look blurry. And the thing is, this is true even if you've got perfect vision. If you've got perfect vision, once you get to about like really close to the eye, it's still going to look blurry, no matter how good your vision is. So everybody has a near point. Near point is the closest you can see clearly. So anything closer than that is going to look blurry. And for typically we want that to be at about 20 or 25 centimeters from the eyes. Because if you're reading a book, for instance, you're not going to hold the book right up to your face. You're going to hold it at a reasonably comfortable distance. So ideally, you want the near point to be at a comfortable distance to hold a book, for example, which is generally accepted as about 20 to 25 centimeters. So ideally, we want this to be about 20 to 25 centimeters. A comfortable distance for holding a book in front of your face. Because if it's more than that, if it's like, let's say your near point is, let's say 100 centimeters, you don't want to have to hold a book way out here in order to read it. You want to be able to hold it at a reasonable distance. So the whole point of corrective lenses, at least as far as farsightedness and nearsightedness is concerned, is that if you can't see these, if you're near, let's say your actual near point is more like 100 centimeters, that's too far to hold a book. So you would like to make the book at an actual distance of 20 centimeters look like it's 100 centimeters away so you can see it. The point of a corrective lens is to turn an object at the ideal situation into an image at a location where you can actually see it. For example, let's say we've got a patient who is farsighted, can see things far away just fine, but cannot see things that are close. Let's say the patient can see far away images just fine, but can't see anything closer than, let's say, 150 centimeters. So we would call the 150 centimeters the patient's near point. And of course, that's not a comfortable location to hold a book. So you'd like to be able to see a book that's at an actual distance of, let's say, 25 centimeters. So let's draw out a diagram of this. Let's say the patient's eyes are right here. So we'll be measuring everything from there. And we'd like to be able to put an object at what location? Yeah, you'd like to be able to put the book at 25 centimeters. So let's say we put the actual object 25 centimeters away from the eye. So this is the actual physical object at an object distance of 25 centimeters. So we'll call that O. But at this actual distance of 25 centimeters, the patient can't see that. The patient can only see things clearly if they are 150 centimeters away. So what we do is we put a lens right in front of the eye. And we can treat this lens as so close to the eye compared to the other distances that it's basically at the same location. But we want that lens to create what? Yeah, we want it to create a virtual image. And why do we specifically want a virtual image? Yeah, for one thing, we want it to be right side up. We don't want glasses that make everything look upside down. And also just in terms of the side of the lens. A virtual image will be on the same side of the lens as the object. We don't want a real image that shows up behind your head. So we want a virtual image, and we want to put the virtual image at a location the patient can actually see. So we're going to want to put a virtual image and the virtual image is going to go at the patient's actual near point. Because if this is 150 centimeters away, then the patient can actually see it. So that'll be the image distance. Since it's virtual though, we're going to use a negative. So that's the whole point of this lens. The purpose of this lens is to take an object at a location the patient can't see, the location we'd like to be able to put the book, and create an image that's far enough away that the patient can see it. And now we know I, we know O, so what should we be able to solve for? Yeah, we should be able to solve for F. And we can use the usual thin lens equation for this. 1 over F equals 1 over O plus 1 over I. And of course, to combine these, we'll need a common denominator. 25 could become 150 if we multiply by 6. No. Yeah, 6. So 6 over 25, 6 over 150. Minus 1 over 150 is 5 over 150. So then we can invert that and get 30. So that means to correct this patient's vision to normal, we need a lens whose focal length is positive 30 centimeters. And positive 30 tells you us what kind of lens. Yeah, we're going to have a converging lens with focal length 30 centimeters, and that should do the trick here. So that works if the patient has difficulty seeing things that are too close, if the patient is farsighted. The other extreme, nearsighted, if you can't see things that are far away, again, ideally, you'd like to be able to see something that's infinitely far away. So you'd imagine an object infinitely far away, and you want the lens to create an image that is closer, an image at the patient's actual far point. So turning an object at the desired far point, infinitely far away, into an image at the patient's actual far point, which again is going to be negative because it's a virtual image. And then you can solve that for the focal length. Any other questions on the optometry stuff? Yeah, let's try it out if it's the other way around. If the patient has difficulty seeing far away things, let's say we've got, say, a mountain that's very, very far away. So we've got, the object is this mountain that is so far away, we're going to treat this as effectively infinitely far away. So we'll say in this case, the object distance is effectively positive infinity. But let's say the patient cannot see something that's very far away. Let's say the patient can't see objects further than, let's say 10 meters, so 1,000 centimeters. Ideal far point would be infinity. But the patient's actual far point is 1,000 centimeters. So we want a lens that's going to take this object that's infinitely far away, or very, very far away, and create an image that's closer. We want a virtual image, again, virtual because it's right side up and on the same side of the lens as the object. And we want that to be an image distance of, we want it to be just 1,000 centimeters away, so it's close enough that the patient can actually see it. Since it's virtual, we'll call that negative 1,000. And now if we plug those into the thin lens equation, we've got 1 over I plus 1 over O, which is infinity. But what's 1 over infinity? Yeah, 1 over infinity is just 0. So we're left with 1 over F equals just negative 1 over 1,000. Invert both sides and we get a negative 1,000 centimeter focal length. And what does that negative tell you? Yeah, you got to have a diverging lens, and the focal length is just going to be the distance to the patient's actual far point. So I think this one actually ends up being a little more straightforward mathematically because the 1 over infinity just turns into 0. Yes, optical power is just the inverse of focal length. Optical power just means 1 over F. So we just invert that and get 1 over 1,000. Though I think that, yeah, diopters is 1 over meters, right? Diopter, or capital D, just means 1 over meters. So you convert this to meters, invert it, or just leave the 1 over whatever from the original 1 over F. And that'll be the optical power in diopters. But optical power is just another way of writing 1 over focal length. Any other questions on that? All right, then let's get back to the electrical stuff. Last time we were taking a look at what electric field means, in the sense of electric field being the capability of that point in space to exert a force on a charged object. If you, for instance, if you know the electric field at some point in space, that's the ratio of force felt by the test object divided by test charge. Or if you put it the other way around, force that's felt by the test charge is the electric field at that location in space times the charge of the test object. And Keep in mind that we're basically treating this as a two-step process here. Instead of just thinking of it as, like, let's say you have a couple of charged objects. Let's say charge A and a charge B. Of course, what's really going on here is charge A and charge B are exerting forces on each other. But it's useful to think of this as, instead of just thinking of it as A exerts a force on B and B exerts a force on A, we think of it as object A creates an electric field in the space around it. And then the electric field from A creates a force on object B. If we treat A as the source object and treat B as the test object. So object A creates electric field in the space around it, then that electric field creates a force on object B. Last time we were taking a look mostly at the electric field creating a force on object B. That's governed by the idea that the force equals, in this case, the force on B equals the charge of B times the electric field from A. So A creates an electric field at every location in space around it, but we only really care about this location. And then to find the force that object B experiences, we take the electric field that A creates and multiply it by the charge of object B, the test object. Any questions on that so far? And then we also need an equation to figure out how much electric field does A create. And this is the equation that somebody mentioned earlier, that the electric field, at least the magnitude of the electric field, ignoring direction for the moment, magnitude of the electric field is K times Q divided by R squared. So Q here is the source of that charged object, the source charge, or the charge of the source charge. And then R, what does R represent in this case? Yeah, the distance. Specifically distance outwards from the source charge to the location of interest, which is typically going to be the location of some test charge. But R is just distance away from the source charge. So the further you are from the source charge, the weaker the effect is going to be. And the larger the source charge is, the stronger the effect is going to be. And then K is the universal electrical constant. And I forget the exact value of that, but you can look it up. It's just a constant to make the units all work out right. So this formula should work for telling you how strong the electric field is, but only if the source is just a single point. So this is the electric field from a point source, a point charge. Point charge in the sense that this charge is condensed into such a small space that you can treat it as a single point. And of course, there's nothing that truly a single point. For instance, even like protons and electrons take up some space, but it's such a small amount of space compared to the other distances involved that we can treat it as a single point. So typically, if you wanted to figure out, for instance, the force that A exerts on B, you'd use KQ over R squared to figure out the electric field that A creates at this location. Then take that electric field, multiply by charge of B, and that tells you the force on B. Any questions on that so far? And then where this gets somewhat more complicated is if you're looking at several source charges. For example, let's say we have let's say we've got charge A, which is positive 5 coulombs. And let's say charge B, which is negative 3 coulombs, and charge C, which is -4 coulombs. And let's say these distances are 3 meters and 5 meters. And let's say in this situation, we want to find the force on object B. How would you go about finding the force on object B here? That is the force that B experiences from charges A and C. Yeah, exactly. I would start by finding the electric field at this location caused by objects A and C. And then once you know the electric field, what could you do? If you know the electric field, how do you find the force? Yeah, we add up the electric fields to find the total electric field at that location and then multiply by the charge of object B. So what we're basically doing here is we're treating both A and C as the test object, or sorry, source object. A and B are the source charges in the sense that they are creating some effect. In this case, creating the electric field. And we're treating B as the test charge in the sense that it is experiencing some result from that electric field, experiencing a force from the electric field. So what I would recommend here is ignore object B entirely. Just treat that as an empty point in space. I'm going to make a note here that charge B is -3 coulombs. We'll come back to that later. But let's just pretend object B is an empty point in space for now. So this is location B. And we want to figure out the electric field at location B. And as you said, we can figure it out for each one of the source charges separately. So for instance, object A is going to create electric field, ignoring C entirely for now, just looking at object A. A is going to create electric field at B in which direction? Yeah, should be to the right, because a positive source charge creates electric field outwards. And that's outwards in all directions. But we only care about at this location. So at this location, outwards means to the right. So this would be the electric field contribution caused by A at location B. And to figure out how strong that is, we can use the usual KQ over R squared. So that'll be K times the charge divided by the distance squared. 5/3 squared would be 5/9. So you get 5/9 K, and then the units would be coulombs per meter squared. So that's EA. EA is 5/9 K coulomb meters squared. And again, that K is the universal electrical constant. What about for C? C is going to cause electric field in which direction? Yeah, should be downwards. A negative source charge creates electric field pointing inwards towards itself. So that means that at this location, we would expect an electric field towards C, which means downwards. And that should be, again, K times charge. And I'm going to treat charge as absolute value here because the negative sign here only affects direction of the electric field. We've already established direction. So looking for magnitude, I would ignore the sign. K times absolute value of the charge divided by distance squared. So that'll be 4/25 times K coulombs per square meter. So that would be the electric field caused by object C. And now what do we do with those? Now that we have both of the electric field contributions. Yeah, vector addition. And note that this means we can't just add 5/9 plus 4/25 because they're not in the same direction. We've got to add these as vectors. By the way, have you seen the parallelogram shortcut for adding two vectors that are drawn from the same starting point? Where if you've got like, let's say, this vector and this vector. Because normally you'd add vectors head to tail. But we could just imagine taking this vector and sliding it up to here, making a parallel. Or taking this vector and sliding it over to here, making another parallel. That forms a parallelogram. And the sum, how would you draw in the sum of those vectors using that parallelogram? That would just be from here to where? Yeah, out to this point at the opposite corner. So this would be the sum. This is a very useful way of quickly drawing out a vector addition if you're adding just two vectors. It only works for two vectors specifically. If you've got two vectors that are drawn from the same starting point anyway, just complete the parallelogram by imagining sliding one vector up to here, sliding the other vector over to here, and the diagonal is going to be the sum of those vectors. So if we try that here, just imagine sliding this down, sliding this over. We're really just talking about this vector here, the diagonal. So that's a good way to get a visual idea of what's going on. And to be more precise, we would probably want to write these in components. In this case, one of them is purely horizontal, the other is purely vertical. So that makes it a lot easier to write the components. If they weren't, we'd need to use some more trigonometry. But EA here is 5/9 to the right. Strictly speaking, 5/9 K, but we can factor out the K. And no up or down at all. So 5/9 comma 0 times K times coulombs per square meter. And the electric field contribution from C, we've got no X component at all. The Y component is negative 4/25. And again, we could factor out K coulombs per square meter. Then we can add those together, one component at a time. And we would say the net electric field at location B, 5/9 plus 0, 0 plus negative 4/25. And again, we still have the K times coulombs per square meter factored out. So that's the total electric field at location B. Any questions on that so far? And of course, if you want, you could now use the Pythagorean theorem to combine these to find the magnitude of the electric field, and also use inverse tangent to find the direction. But since we're going to need to find the force anyway, we may as well keep it looking like this while we go through the final calculation, which is, how would you turn that electric field into the force? Yeah, multiply by charge B, negative 3 coulombs. So that means the force on B is going to be negative 3 coulombs times this vector, 5/9 comma negative 4/25 K coulombs per square meter. And that negative 3 just multiplies to both of these. So we got negative 3 times 5/9 is negative 5/3. Negative 3 times negative 4/25 is positive 12/25. And the coulombs combines with this coulomb, so we get K times coulomb squared over square meters. So this would be the X and Y components of the force on B. And then we could use that with Pythagorean theorem to find the magnitude, how much force B experiences. and also inverse tangent to find direction. If we take a quick look at this geometrically, though, we know the electric field is down and to the right. Which direction would you expect the force on B to look like? Yeah, it should be up and to the left. The negative charge reverses the direction because, again, force is charge times electric field. The electric field here, the total electric field at this point is down and to the right. But to find the force on B, we're multiplying that vector by a negative charge, and multiplying a vector by a scalar reverses the direction. So B is going to experience a force this way. And I think we can see this more conceptually as well. B is a negative charge. It's simultaneously getting attracted towards positive charge A and repelled from the like negative charge C. So it gets attracted to the left and repelled upwards. It's going up and to the left. So that would be the total force acting on object B. And this is a very useful way of doing this. Find the electric field first and then multiply by charge to find the force. One of the reasons this is useful, even though it might seem like adding an extra step, is that the electric field we found didn't depend on what charge is actually here. If we took away charge B and put a different charge at the same location, we wouldn't need to do all these calculations again. We can just use the electric field we already found times the different new charge that we put at that same location. So we're finding a property of the location first, and then applying that information to the object that's at that location. Any other questions on that so far? All right, let's try drawing out some electric fields in more detail then. Because here we've just been looking at this one location. But it's useful to look at sort of mapping out the electric fields at various different locations around a charge or several charges. The simplest possible example, let's say you've got a positive charge versus, let's say you've got a negative charge. If the entire universe consists of just one positive charge, what would the electric field look like? Which direction would you expect the electric field to be? Yeah, we should just have arrows pointing outwards in all directions. And those should be evenly spaced because which side you're on doesn't matter. All that matters is how far you are. So this is one depiction, the field line diagram of the electric field caused by a single point positive charge. You just have electric field outwards in all directions. And note that the lines are getting more and more spread out. In other words, the electric field gets weaker and weaker as you get further away. Negative charge, same idea, except you have electric field pointing inwards instead. So this would be what the electric field, the field line diagram looks like for the electric field created by a single point negative charge. Any questions on those so far? Then let's take a look at some other combinations of charges. To start with, let's say we have two positive charges. Let's say we've got a positive charge here and another equivalent positive charge here, so same size charges. And let's say we wanted to figure out the electric field in various locations around this. For example, let's say we are exactly in the middle. And let me label these. Let's call these charge A and charge B, but they're both acting as source charges. Charge A is creating electric field at this location in which direction? It's a positive charge though, so that's going to be, right, should be away. So charge A creates electric field outwards in all directions. At this point, that means to the right. So that's the electric field from A. But B is also a positive charge. So if we ignore A, B is creating electric field outwards, which means to the left. And if these are the same amount of charge and we're exactly in the center, what does that tell you about the strength of these two electric fields? Yeah, they're equal magnitude, but opposite direction. So when we add those, what do we get? Exactly, 0. So in the exact center, the electric field will actually be 0 if we're exactly in the center. But what if we're closer to charge B? Like, let's say we're here. Which direction would you expect the electric field to be? Yeah, it should be to the left. Because if we're closer to charge B creates a strong leftwards electric field. We're further from charge A, so charge A creates a weaker rightwards electric field. So strong leftwards plus weak rightwards, they partially cancel out, but not completely. The result is to the left, but somewhat weaker. Likewise over here, A is going to be stronger because we're closer to A, so we get electric field pointing to the right. So in between, we get electric field pointing towards the middle, but it gets weaker and weaker because they cancel out more and more, and in the exact center, no electric field at all. So a strong electric field when you're close, gets weaker and weaker, is exactly 0 in the middle. What if we're over here though? At this point, B creates electric field in which direction? Yeah, B is going to create, in general, outwards electric field because it's positive charge. At this point, outwards means to the right. So we get, and we're fairly close to it, so we get a fairly strong electric field contribution from B. Now, ignoring B, A is creating electric field in which direction at this point? Yeah, should be also to the right, because away from A means to the right. But since we're further away, it's going to be weaker. So we're adding a large vector to the right plus a small vector to the right. Those are going to combine to be even stronger. So at this point, we should expect a very strong electric field to the right. And of course, that's going to get weaker as you get further away, because both of the fields will get weaker as you get further away from them. What about over here? Which direction would you expect the electric field to be? Yeah, should be to the left. A strong leftward vector from A plus a weak leftward vector from B leads to an even stronger vector to the left overall. And again, this gets weaker the further out you get. So we now at least have the electric field just conceptually in terms of direction and roughly how strong it is everywhere on the x-axis. Let's try some points on the y-axis as well, like directly above and below. For instance, up here. At this point, again, we should expect each of these positive charges to create outwards electric field. So A is going to create electric field outwards, which means up and to the right. B is going to create electric field outwards, which means up and to the left. Same distance, same strength charge, so we should get same strength electric field. When we add these together, what would you expect to happen? Should be straight up, right? If you add this vector plus this vector, the result is straight up. You could also look at this in terms of components. If you split each of these up into x component and y component, x component and y component, when we add the components, what's going to happen? Yeah, x component to the left, x component to the right, those are going to cancel out. But the y components are both upwards, so those combine to an even larger y component. So at this location, we should expect the electric field to be straight up. And that should actually be true everywhere on the top of the y-axis. We get upwards electric field everywhere in this region. Because if we had been anywhere, we still have that same effect, just at different angles. Likewise, everywhere below, it's going to be pointing straight downwards. And of course, that also gets weaker and weaker. And just sort of, I guess I'm transitioning here to the field line diagrams. Instead of drawing out individual arrows, we can just say the overall trend is to the right. Overall trend over here is to the left. Overall trend straight up, straight down. But also we should take a look at some of the other locations to fill in the details. Like let's say we're talking about a point directly above location B. B is going to create electric fields straight up. But what about A? A is going to create electric field here in which direction? Yeah, up and to the right. And somewhat weaker because we're further away from it. And again, we could use the parallelogram method to add these. Shift this one up and to the right. Shift this one straight up. And we get something like this as the actual electric field at that point. So that's the electric field at that location. And another useful way to think of this is that since we're closest to B, I would think of it in terms of B. B creates electric fields straight up, or at least it would if it were the only thing in the universe. But A is positive, so it pushes electric field away from itself. So looking at just B, B would create straight up electric field. The positive charge A biases it to the right. Likewise, if we were directly below B, we would expect electric field straight down, but A, pushing outwards, biases that further to the right. Or over here, A would create electric field straight down, B biases it outwards, so that's going to be to the left. And likewise up here, A would be creating electric field straight up, B pushes outwards and biases it to the left. So we'd expect something like that. And we could keep putting in more and more pieces of information here. We could say, for instance, right here, A or B would create electric field up and to the left. A biases it outwards. So it would be something more like this. And you could just keep filling in more and more detail. But eventually, once you've got enough detail, you can start connecting these arrows with more curves, much like these ones. But it's going to end up being sort of curving like this. Keep in mind the field lines should not cross each other. If you've got field lines crossing each other, you've got a problem. Because the whole point of a field line is you can draw in vectors tangent to that field line. If you've got two field lines crossing, then you're saying that at this point, the electric field is this way and this way at the same time. And that doesn't make sense. Just like a function has only one output for each input, a vector field should only have one vector for each location. You can't have field lines crossing because that suggests two different vectors at that location. So keep that in mind as you're drawing these. Field lines should not cross each other. If you've got a field line going up and to the left, it's going to have to curve so it doesn't cross this one. In fact, this one should end up being an asymptote. Another good way to draw this out, now that we've got some basic detail, we know that each one of these should have field lines coming out of it. To start with, I usually draw 8 just through the 8 cardinal directions, north, south, east, west, northwest, southeast, and so on. So if you just have 8 little arrows coming out of this one, we've already got 2 of them taken care of. And same thing for this one, evenly spaced. And then ask yourself which way they would go. For instance, this one would go straight up if A were the only thing in the universe, but what's B going to do to that one? It's going to bias it in which direction? Instead of going just straight up, B is going to make it go up and to, yeah, it should be up and to the left. So instead of going straight up, this one's up and curving towards the left. Likewise, this one will be going straight down, but B's outwards push causes it to go down and to the left instead. And same thing here. We should expect complete symmetry of the electric field. In general, if the arrangement of source charges is symmetric, then you should expect the electric field it creates to be symmetric as well. Likewise, this would be going straight up and to the right, but A biases it more to the right. So it's going to curve more like this. And same thing here. Likewise, this would go straight down and to the left, except B pushes it further to the left. So we get something more like this, and likewise this one. And then these diagonals are going to be a little trickier. This one we should expect to go up and to the left, but A pushes it more to the right. So it's going to go out and to the left, but curve ending up with sort of an asymptote here. And same with this one, and this one, and this one. So this gives us a pretty good diagram of what the electric field caused by these two charges together would look like. And we can see from the closeness or spread outness of the lines that in the center, we're going to get a very weak field. The electric field lines are spread far apart. Likewise out here, they're spread apart, so we get a fairly weak field. In this region and in this region, though, we're going to get very strong electric fields. So you can tell from the diagram where, not precise numbers, but just general ideas, relatively speaking, of where you would expect the electric field to be stronger versus weaker. Any other questions on that? All right, to get some more practice on this, I would recommend trying this again with two negative charges is pretty much going to be the same thing, but everything's inwards instead of outwards. But it can still use some good practice to draw it. And also try drawing it out if one of them is positive and the other one is negative. That's going to lead to a completely different shape. So try that out as a challenge. See if you can draw the electric field that would be created by a positive charge and a negative charge. And if you want to check what that looks like, look up electric dipole online. See if you can find a picture of the field created by an electric dipole. But try drawing it first to get some practice. All right, feel free to email me if you have any other questions, and I will see you next week. You're welcome.